So here if you put the values and if you draw the waveform, you will be getting some waveform, this type of waveform. At your at pi by 2 you are going to get Vm upon omega L, and at 2 and at pi you will get 2 Vm by omega L. So similarly if you plot for 3 pi by 2 and uh, 2 pi, you will get a waveform like this. So this, the value will be like this only. It, actually the waveform will show you the nature why we are saying inductive load is very difficult to understand. The instability is caused because of the, okay, so this is how the nature of the waveform goes on. Like here 3 pi by 2 you will get 2 Vm upon omega L, this is the value, and your at 2 pi it will it will be going to 0. So your current, if you draw the current waveform, your current waveform is I naught upon omega t is your always remains there, means from 0 to 2 pi, because of the current is always there, your diode never turns off. That means your diode is always conducting for an inductor, for an inductive load. Okay, if your diode is conducting, then what about your, if you draw the V naught, that is your output voltage. So V naught, using KVL, you will write V naught is equal to Vs. So V naught will be zero. V naught will be like a sinusoidal waveform. So V naught will be pure sinusoidal waveform. So it will have both the cycle, positive half as well as negative half. Because the shape of the waveform will be, it is continuously on, so it won't get off for the next cycle also. Okay, what about your Vd? If your diode is on, Vd is the voltage across the diode, so diode voltage will be equal to 0. It is always shorted, so you can draw the waveform like straight line. Okay, now this is the nature of your load. uh, in your, if you find out the if you find out the resistive load, there you would have seen that the diode does not conduct for the negative half cycle, but for an inductive load the diode conducts for the negative half cycle. And regarding the shape of the waveform, if you see the shape of the waveform between the output voltage V naught and I naught is different. Okay, that's why we are saying this load is a, you can say, current stiff load. And always remember, this is the very important with respect to power electronics. This load, inductive, pure inductive load, is very important. Okay, so you must have to focus on how we have derived this thing. Now, talking about the values, so let's first discuss what will be your this I naught. If you have to take out the value of I naught, if you have to take out the value of I naught, and that will be your average value. I naught average value will be equal to, if you see the waveform, 1 upon 2 pi integration 0 to 2 pi. What is the waveform equation? Vm by omega L and 1 minus cos omega L. d omega L. So this is the I naught equation. You integrate it from 0 to 2 pi, and you will get the answer Vm by omega L. Okay, because here you will get integration of one will be omega t, and integration of cos will be sine omega L omega t. If you put sine omega t, the limit is 0 to 2 pi. If you put this, will be completely 0. Okay, you will have to left with only one term, that is Vm by omega L 2 pi. So if you have good maths, you will be able to do this. Okay, next. And next is the what will be your RMS value, I not RMS for this waveform. So this again I am leaving it to you how you are calculating the RMS value. Okay, and what about your voltage, this output voltage. So output voltage will be, if you it's Vm by root 2. I can directly write Vm by root 2 because your output voltage is similar to the supply voltage. Sinusoidal waveform is there, so it will be Vm by root 2, the RMS value of that. Okay, uh, one more question is that, if you can, let's if you are able to